The limit state design. How do you design a structure? The design of any structure can be performed by keeping in mind the following two important conditions. Every structure that is designed should satisfy these two conditions. First is safety and the second is serviceability. Let us discuss about each one of them briefly. How do you say that a structure is safe? How do you ensure that a structure is safe? A structure is considered safe if the possibility or chances for collapse of the structure is very low. Collapse chances are very low when it is subjected to service loads and probable overloads. What are service loads? Service loads are usual expected loads on the structure which it is subjected to in due course of time. What are probable overloads? These are extreme loads which might occur very rarely, such as winds and earthquakes. Now, what are the different ways by which a structure can fracture or collapse? By exceeding the strength of the material or by exceeding the load bearing capacity, a structure can collapse. By sliding or by overturning or by buckling or fatigue or fracture. So these are the different ways by which a structure can fail and become unsafe. Now coming to the aspect of serviceability, this is another most important aspect which should be taken care of while designing a structure. It is not just important to ensure a structure is safe, it is important as well to ensure that the structure is serviceable too. How do you ensure it? Any occupant or the user who is using the structure should feel comfortable while he is using that structure. If the chances of user discomfort is acceptably low, then we say that the structure is serviceable. Okay. And what are the factors which affect the comfort of a user? The deflections of structure, the large cracks occurring in structure, vibrations in the structure can actually make the user afraid. It doesn't seem comfortable for the user. Further, other factors involve the loss of durability, the loss of impermeability, and the lack of fire resistance. And these factors also affect the comfort of the user. So it is very important that not only safety but also serviceability is important for a structure as far as its design is concerned. Now coming to the two important terminologies, characteristic strength and characteristic load. What is characteristic strength? We have already discussed about characteristic strength in detail in our previous lectures. It is the strength of the material below which not more than 5% of the test results are expected to fall. That is, there are 95% or more chances to get a strength value of a mix greater than the characteristic strength. Now, what is the characteristic strength of concrete? We have already learned that it is the 28-day characteristic compressive strength of concrete cubes of size 150 mm. But when you design a structural member, it is not just enough to take FCK or the characteristic compressive strength of concrete cubes as the characteristic strength of concrete. Instead of FCK, we adopt 67% of FCK only. We take only 67% of FCK. We consider that the structure is having a strength of only 67% of FCK, not FCK. Why? Because it is very difficult to ensure complete quality control in the construction of concrete structures, unlike the construction of concrete cubes in laboratory conditions. So that is why, unlike the cubes having a strength of FCK, it is difficult to ensure FCK strength in large structures. So we take only 67% of FCK. Now coming to the characteristic strength of reinforcing steel, we take the characteristic strength of reinforcing steel as equal to yield strength of steel in case of MS bars or Fe250 grade steel. But for those grades of steel where the yield point is not defined properly, we take 0.2% of proof stress as its characteristic strength. Now coming to the case of characteristic load, Characteristic loads are those loads which have 95% probability of not being exceeded during the life of the structure. Such loads are defined based on the following codes, IS recommendations given here: IS 875 part 1, 2, 3, 4 and 5, giving details of loads, dead loads, live loads, wind loads, snow loads and combination of loads. Further, the IS code IS 1893 also gives the load details when a structure is subjected to earthquake loads or seismic loads. Before we go into the details of limit state method, we should know and define what is meant by limit state. As the name suggests, limit state is a limiting state of the structure. It is a limiting state of a structure beyond which the structure no longer becomes safe or serviceable. So the serviceability and the safety requirements of a structure just before the failure occurs is ensured by limit state. So limit state is that state of a structure beyond which the structure is no longer safe or serviceable. Okay, and in terms of the textbook definition, a limit state is a state of impending failure beyond which the structure ceases to perform its intended function satisfactorily, either in terms of safety or in terms of serviceability. Okay, now let us define the types of limit states. We have two types of limit states: ultimate limit states or limit state of collapse, and serviceability limit states. The ultimate limit states are explained in terms of the strength of the structure, or if the structure undergoes overturning or sliding, buckling, fatigue or fracture. So any of these can result in the failure of the structure, and these limiting states are called ultimate limit state of the structure. Now coming to the serviceability limit states, as we already discussed that the serviceability limit states are those which renders the structure discomfortable, makes the structure discomfortable for occupancy. And what are such limit states? Excessive deflections, crack width, vibrations, leakage, loss of durability, etc. Now the method of limit state is actually entrenched upon all the above aspects, and here we perform two things which are very important. First is the underestimation of the material strength, and second, the overestimation of external loads. So these are the two important points being observed in limit state method. First is the underestimation of the material strength, by which we mean the material strength which the material actually has will be underestimated. We will reduce the material strength at the time of design. Further, we perform what is known as the overestimation of external loads. The external loads acting on the structure will be overestimated, or in short, we mean the external loads are enhanced. We increase the external loads at the time of design. So the purpose of doing this is to ensure that the structure is very safe. Okay. Now, for the purpose of doing underestimation of material strength and overestimation of external loads, we use what is known as partial safety factor. Partial safety factors are those factors of safety which are individually applied to separate materials and separate loads. And with the help of these partial safety factors, we can ensure that the structure has adequate safety at ultimate loads and the structure has adequate serviceability at service loads. Here we discuss about the two aspects: design strength and design loads. The strength and the load values used in the design are known as design strength and design loads respectively. So how do we find these out? We already studied that the strength of material is underestimated in limit state method, for which we have to underestimate or reduce the value of strength of the material. That is why design strength is equal to characteristic strength of material divided by partial safety factor for the material, where characteristic strength of material are separately given as equal to 0.67 FCK for concrete, and the characteristic strength of steel is taken as the yield strength Fy. Now, what about partial safety factor for the materials? We have separate partial safety factors for materials. It is equal to 1.5 for concrete and 1.15 for reinforcing steel. The partial safety factors chosen for concrete and reinforcing steel are different, and is found that the concrete has a greater partial safety factor than for reinforcing steel. Why is it so? We must understand that the construction of concrete in the field cannot ensure so much quality control as that happens in the manufacture of reinforcing steel in the industrial conditions. Finally, we determine the design strength of concrete as equal to the characteristic strength of material divided by partial safety factor of the material is equal to 0.67 FCK divided by 1.5, which we get it as 0.447 FCK, which may be approximated as equal to 0.45 FCK. Similarly, we determine the design strength of steel is equal to the characteristic strength of steel divided by partial safety factor for steel equal to Fy divided by 1.15, which we finally obtain as 0.87 Fy. And now, how do we determine the design loads on the structure? We already studied the principle behind LSM that the loads on the structure are overestimated. So we have to enhance the load on the structure. The characteristic loads as obtained from the Indian Standard Recommendations IS 875 and 1893, we have to multiply them with the partial safety factor for the corresponding load. Each load will have a separate partial safety factor which should be multiplied by the characteristic load to obtain the design load, thereby enhancing the load on the structure. The partial safety factors in this regard are obtained from table 18 of IS 456, page number 68. Now let us study about the stress strain behavior of materials and how it is used for the design. First, we deal with concrete. Concrete, as you know, in flexural members, concrete gets subjected to both compressive stress as well as tensile stress. The concrete on the tension side is generally neglected because the tensile strength of concrete is very small compared to that in compression. On the compressive side, how the concrete behaves is what is shown from this stress strain diagram. So here first you observe the characteristic curve. This is the actual stress strain behavior of concrete when subjected to flexural compression. As you increase the load, initially the stress strain behavior is linear, it is a straight line initially, and later it becomes non-linear, and at a particular value of strain equal to 0.002, the stress strain behavior becomes flat and parallel to the strain axis, and it continues up to a maximum strain of 0.0035, and this is the ultimate compressive strain in concrete. And the maximum strength or the maximum stress that can be achieved by concrete in structures is 0.67 FCK, this which we have already discussed. Now, for the sake of design, as we already discussed, we have to underestimate the strength of material. Every stress value in this characteristic curve has to be underestimated. So we have to use a factor of safety. The partial safety factor for concrete is taken as 1.5. We already discussed that. So every stress value on this characteristic curve, if divided by the partial safety factor 1.5, the final curve which you obtain is the design curve. So the design curve is the curve which is obtained by applying the partial safety factor on the characteristic curve. The characteristic curve is the original curve, and design curve is actually derived from the characteristic curve for the sake of design. So the ultimate stress in the concrete 0.67 FCK becomes 0.45 FCK. Now let us discuss about the stress strain behavior of steel. We have two kinds of steel, Fe 250 grade, which is the MS bar, and HYSD bars, Fe415 and Fe500 grade steels. Now we want to understand how the steel behaves when subjected to axial tension. You know that steel is used on the tension side of flexural members and it is subjected to tension. The behavior of steel in compression almost resembles that of axial tension. So we have written it as axial tension or compression. Now let us study about the stress strain behavior of Fe250 grade steel. You must observe the characteristic curve, which is the original stress strain behavior of steel. We have neglected the strain hardening regions beyond this. As you increase the load, the stress increases proportionally with strain up to a maximum stress value equal to yield stress, at which there is no increase in stress with increase in strain. So this is characteristic curve of Fe250 steel, and you want to obtain the design curve, for which you need to underestimate this curve, but underestimation is not done in the initial portion because the modulus of elasticity of steel is always constant. Whether it is characteristic curve or design curve, the modulus of elasticity or the slope of the initial portion of the stress strain curve is always constant in case of steel. So you need to underestimate the characteristic curve only beyond the yield point. So the stress value corresponding to yield point is underestimated and you get it equal to 0.87 Fy. The stress in the design curve is 0.87 Fy, that is the maximum stress that can be attained as far as design curve is concerned. And what is the corresponding strain value? The corresponding strain value is equal to 0.87 Fy by Es, where Es is the modulus of elasticity of steel. Now coming to the HYSD bars, Fe415 and Fe500 steel, let us see how they behave when subjected to axial tension or compression. We know that as the load progresses, initially the stress strain behavior is proportional, but beyond a certain point the stress strain behavior becomes non-linear, and at a point equal to yield stress the curve becomes flat and further increase in strain does not cause increase in stress. In order to obtain the design curve, as in the previous case the initial portion is kept untouched, we change or underestimate the stress values only beyond the non-proportional region. Up to the proportional limit or the proportional region we do not change the stress value, we do not underestimate the stress value, we underestimate the stress value beyond the proportional limit. This is the proportional limit, and only beyond which we perform the underestimation of stress. So every stress values on the characteristic curve after the proportional limit is divided by partial safety factor and underestimated, and finally we obtain the design curve, and the maximum stress in the design curve is 0.87 Fy. Now what is the strain value corresponding to 0.87 Fy in the design curve? It is equal to 0.87 Fy by Es plus 0.002.